So we're going to do a couple of problems. We'll start with this one. And don't think so much like, what am I supposed to do? How do I do this problem? Think about, what are they asking me? What do I need to know? Just figure out all the stuff that I need to know. See if I can find that as a given. Is it something I can calculate and get there? Okay. So we want to know what percent of the pool is filled. Okay, that's a volume question, right? Right. So we take the volume partial volume over the total volume, right? That's percentage times 100. That's percentage. Agreed. Okay. So we need to find the partial volume and the total volume of the entire pool. So let's look at the partial. How do we calculate that? No. We don't need to. We can write it. And there's formulas for the volume of a general prism. We don't need that. We're not dense. You should find the volume of this water. Look at this water. Look at what kind of shapes we can take advantage of. Triangles. There we got it. Depth. It's a right triangle. Okay, that's maybe useful. Rectangle along the back side here. That's a rectangle. Okay.
Yeah.
Notice the shape of the water. It is a triangle on this side. It's an identical triangle on this side, and it's just straight shot. Like, what you call it? You call that a prism. Okay. It is the same on the front and the back, and it's just a straight shot between the two. You call that a prism. It's called a triangular prism. Okay.
I bet there's a formula for that.
Or there's just common sense.
Oh,
Don't
geez.
you, since it's like 1 meter high on that side, if you just like chop off a whole meter of the top, yeah, then that's a triangle of 2 meters in the base and 12 meters is the height.
Okay.
And then you can further, those are similar triangles. No?
Yeah, oh, they're similar.
Okay.
They're similar. We're just looking for what percent of the pool is filled. I mean, maybe you didn't take note. It's 1 meter deep. Or sorry, 1 meter deep, 3 meters deep, 12 meters, 6 meters wide, 1 meter deep, shallow, and 3 meters deep at the deep. Water is being pumped in the 1 meter of water at the deep end. So
Yeah.
this is 1.
But what do
This-
you need to know the height in order to find?
Oh, you need to know this. Oh, okay, so you, alright, I see what you're saying. So you're saying that this triangle and this triangle here are similar triangles. Yes. You're right about that. So this guy right here, the partial would be the volume of this water here. This triangular prism. Whoops. Forget about that. So we need to know, this is 1, and we need to know how big this is. Well, if this is 3, right, and this is 12,
Except it would be 2.
sorry, 2 and 12, right, then if this is 1, this would be
6.
Oh, right.
6. Yeah, they're similar triangles, 1/2 of the height, or whatever you're gonna call it, 1/2 of this. This measurement would also be half of this guy here. So this is 6. It's not depth, I don't wanna say depth, but it's length, width, whatever. How much is that? That's also 6. So I have a shape that is a triangle on both sides. It's a prism. How would I find the area of such a prism shape?
Area of the triangle
area of the triangle times 6, right? Pretty basic. So you find the area of this triangle, can you find the area of that triangle? It's 6. The area of the triangle is 6. It's 3, it's 1/2 base times height. Right? 1/2 times 1 times 6. Okay. Well, that's the area of the triangle, and then we'll multiply by the 6 along here. And another 6. 18. Right, 6 times 1/2 is 3. 3 times 6 is 18. 6 divided by 2 is 18. That's 18 over 18 over the total volume.
Eighteen times 6.
18 times 6.
Yeah, because, oh, never mind, that's not a total triangle.
So we got a triangle that we could look at. Right, I'm just drawing a straight side view of this tank. Right, we got a triangle part that is 3 by 6, 12. 3 by 12. And then a rectangle which is 12 by 1, right? I'll see that. We can find that area and then multiply it by the width of this pool.
Yeah.
You got 3,
18.
so that's, here is what?
18.
This is 18 and this is?
6.
Let's see, 1/2 base times height. Let's see, this would be 1/2 times 12 times 3, right? That's the 18. And 1, what's times 2?
That is times 2.
It's not 3.
Yeah.
Oh.
Good. And then this is 1 times 12. That skinny rectangle along the top. Could you now fill the blue, green, and pink colors together? Okay. So we got the total area of the cross section is how much? 12 plus that is what, 24 you said?
Oh, plus that. Oh, okay.
This plus this?
Alright.
12 plus 12, 24. So the total volume is 24? Alright, so what percentage? 18 divided by 24, 100. What's our percentage?
Wait, is that's not the total volume,
Isn't that just the area of that?
Oh, sorry, 24 times. 24 times 6 is the volume, which is 144. Alright, we got a volume of 18, we got a volume of 144. We divide and multiply by 100, you get what? So 13%. What does the percentage say? 12.5%. Oh, they even make that. 12.5%. I'm gonna guess that whoever wrote this problem was just trying to get you to think about how would I find the volume of this tank? Right? Getting you to realize that it's just the area, surface area, times the width. Simple as that.
Does that apply to all prisms?
All prisms.
So it's just the area of one face
Mhm.
times the width?
Does
Okay,
that make
sweet.
sense? Yeah?
Oh, I mean, to me, like, that sounds really weird, but like, that's just cause like I'd have to have it all put in front, but like.
Well, how about, think about, I'm gonna draw a little more accurately, so come over here and draw a box. The mistake that is made by lots of math students is they think that good mathematicians are good because they memorized all the formulas. It's not why they're talented in mathematics. They're thinking about, what do I know, what do I wanna know, what do I need to know to get there, okay? So if I want to find the volume of a plain old box, length times width times height, right? Well, that's length times width. What's length times width?
That's what it
The
is.
area of this thing, whatever the length and width come out to be, right? What's area? What is area? Length times width? No. What is area?
The inside the length, like that.
The space takes up. Oh,
Which colors did you say again?
blue, green, and pink. Blue, green, and pink. Well, couldn't area be measured? Well, area that we're associated with, that we use all the time, is how many squares fit in a certain area, right? How many squares?
Oh, okay, this makes sense. now.
What's volume? How many cubes fit in a certain three-dimensional space? How will I figure out how many cubes fit in here? Well, I'll take the number of squares
Times the.
times the number of whatever units there are along here, right? 1 unit high will give me this many squares, or cubes. 2 units high will give me twice that many cubes. 3 units high will give me 3 times that many cubes, and so on and so on and so on. It's counting the cubes that way, right?
That was a
Surface
gorgeous
area.
math moment.
What's that?
That was a really pretty math moment.
Yeah.
Because I never understood that. That's cool.
So that would apply to any prism, right? It could be any crazy looking shape, as long as that shape is the exact same, whoops, up here, right?
Straight shot.
What's that?
So then it'd be like half blocks.
There would be, but a quarter of a block times the height of one is a quarter of a cube, right?
Yeah,
Yeah.
such a cool shape.
So it doesn't really matter that we get all these little pieces of squares. Like, pick one. Let's say that this guy is it doesn't look quite right, but let's say it's like a half a square, right? It doesn't really matter that it's a half a square. When I multiply by that by a height of 1, if I have a half a square and I multiply by a height of 1, won't I have a half of a cube?
Yes.
And if this is a quarter of a square, won't I have a quarter of a cube when I multiply it? If this is an eighth of a cube, I multiply by a height of 1, I get an eighth of a cube, right? Every square unit translates directly into a cubed unit when we have a full 1 height, right? And if it's a height of a half, right, then a half of a square multiplied by a height of a half will be a quarter of a cube. Right? So we're just taking the surface area, and when we extrude that along this path, this vertical path, this straight path, like that height just draws out all the cubes that we'll get in that volume. Right? So come back here. Yeah, any prism at all, you just take the surface area of one side, multiply it by that straight path. It extrudes it to the other side. Okay? So, not a formula, right? Or if it is a formula, like every human being should get credit for it because it's right there. You know what I mean? It's right in front of your face. Take the surface area, multiply it by the height. And it tells you how many cubes that it takes up.
So then how would it work, like, per se, if it was a pyramid shape, or it wasn't consistent all the way up?
So that's different. And there are ways we can look at that. We can create formulas using calculus. But in general, like the general pyramid shape would be 1/3 of the prism that it contains. Okay, so if we're talking about well, it's not as easy to see. Okay, but this pyramid, okay, it could fit inside a box, right? A box that has the same base and I don't know, length and width and height, those 3 same dimensions. Okay, So if we were to just perfectly put a lid on this guy that was the same size as this, okay, so something like this. This pyramid's fitting inside of this box perfectly. The very tippy top of this pyramid is just touching the top of the box. Well, the box is going to be length times width times height. And the pyramid inside there. No matter what it looks like, it may have to be centered in the top of the box. It could be anywhere. It's going to be 1/3 of that box. 1/3 length times width times height. And it works for this guy too. Just this weird wavy thing. Okay. Anything that comes to a point, say right there, right? And this kind of wavy. Okay, makes this pyramid. Well, we just looked at the prism, right? Surface area. So we're just taking, I guess we'll talk about the surface area. This guy's a little easier than that. Surface area times the height is the volume. And that pyramid takes up 1/3 of that. 1/3 of the surface area times the height. Every time. Pretty cool. All right, so back to our related rates model. I think they're just with part A, just trying to get you to start thinking about what is the volume of this prism, okay? And it's not that difficult. I'm going to copy this slide. And we'll do part B now. Okay, so part B. You have to think about what things are given and what are you looking for. Okay? I want to relate things that I know and things that I want to know. This is the hardest part. I said last time. Okay. And the thing that I want to know is, it has to do with it has to do with the rate of change of the what? The water level of the height of the water, right? Okay. What's that in terms of calculus? Sure. The rate of change. If this is called H. Rate of change of H with respect to T. So we call it dH dt. We want to know dH dt, right? What is that? What is dH dt at any given moment? Is it consistent? No, it's not, because if the same amount of volume is coming in, that volume has to spread out now across more and more and more area the higher the height is. And that surface area of the top is changing because we have this shape of a swimming pool. So all that is to say, dH dt is changing all the time. It's different from 1 second to the next second. So we want to figure that out. You want to think, naturally, this rate of change is going to be in some equation at some point with some other rate of change. Does that make sense? We're going to take a derivative of some function. Our rate of change that we want to know is going to need to be in an equation with a rate of change, with another rate of change. And this rate of change needs to be one that we know. We need to know this rate of change. Does that make sense? We need to know what that rate of change is. Okay. So is there a rate of change that we know? Water being pumped in. So what about the pool is changing with that 1/4? The volume. That 1/4 is it's directly a measurement of the volume that's being added, right? So what is that in terms of calculus? dV dt. We want to know dH dt. We know dV dt is equal to 1/4 At its very simplest, a related rates problem is one where I have an equation that has dH dt in it. dV dt is also in that equation, and I can replace dV dt with 1/4. Right? It's all about solving for the variable. To solve for one variable, you need all other variables to be replaceable. Replace them with numbers. Okay? So you're going to write an equation that you're going to take the derivative of. And the derivative is going to include dH dt and dV dt. And you need an equation that has the height of the water and the volume of the water in the same equation. Is there a relationship between the height of the water and the volume of the water? Absolutely. Maybe we can just write it down. The volume of the water is equal to
Half base height.
so half
12H.
of B times H times
Width.
which is
Times
6. 3BH. 3BH.
But that's not all of it.
What's that?
That's not all of it.
That's just the
That's
trash.
just,
No.
What are we saying?
that's just, that's not the volume of the creek here.
Which whole thing?
The whole pool?
Oh, of the whole pool. Do we care about the volume of the whole pool? Think about what the water is. It's only in the part of the pool where this does describe the volume. Right? It's at a height of 1 meter. When it's at a height of 1 meter, is it in this upper part? No, so we don't have to worry about that the volume of the pool can't be just simple area of the triangle times the width. The area of the volume of the water can be calculated that way. Does that make sense? An important fact here is that there's 1 meter of water at the deep end. At that very instant, that's what we're talking about. We're not talking about other times. We're talking about the very instant that there's 1 meter. Now, if I look at the diagram, if there's 1 meter of water, well, the height of the triangular part of the tank is 2. So the instant that we have 1 meter of water at the deep end, we don't even have to worry about this top part, this little 1 meter part. We don't have to worry about that. We would have to take that into account if we wanted to find the volume of the whole pool. We don't want the volume of the whole pool. We just want the volume of the water itself and the height of the water itself. If the water were higher, if it was later, and the water did start to come up into this part of the pool, now we have to worry about it. But at the instant, we only have 1 meter deep in the deep end. We're only in the triangular part of the pool. Right?
Yes.
Okay. Now think about it.
No, yeah.
If we were in the non-triangular part of the pool, the rate at which the height is changing would be very boring. We wouldn't even need calculus, right? You understand what I'm saying? Because once that shape is just a box, when you just start filling it with the same, like your volume is changing at a steady rate, then your height is changing at a steady rate as well, right? Because that box, that is simple base times length times height, base times width times height, whatever you want to call it. Like, it's just a box, you're filling up a box with water, it's gonna change, or a prism, if you're filling a prism, like where from top to bottom, not like on its side or something, then that rate of change of height is gonna be constant. It'll be easily calculated. So, the rate at which the height is changing is only itself changing when the surface area there is, changing. I don't know, a whole lot of an easier way to say that without saying changing for 3 times. Now, can we all take the derivative of this function? Yes, we can. We could do that. We could also, if we want to go to the next level of related rates, we just think ahead a little bit. Look at this h, right? That's what I want to know about. How fast is that changing? Correct? If I take the derivative of this, I'm going to have some b's and dv, dt's in there. Do I care or do I know anything about the base and how fast it's changing? And by base we mean this measurement right here. You know anything about that? Are you told anything about that? You asked anything about that?
It's 1 meter.
This is?
Right.
This guy right here?
Oh, that's 6, that's 6.
Oh, approximately.
Okay, it is 6, but it is changing. Remember what I said, you may remember, you may not. You don't plug anything in here. That changes, right? If it's changing, you only plug it in once you have the derivative. Okay, then you can talk about that instant. But if I make the base 6 right here, then it can't change. You know what I'm saying? It can't change if I make it be 6. Then it's 6 always. Even when I look at the rate of change, it's always 6, which isn't true. But if I take the derivative now with b and h, I'll have b's and dvdt's. I don't really know anything about them, and I don't care anything about them. Even if I can figure out how fast this is changing, I don't care. I'm not asked how fast that's changing, right? Okay. So I will bet you like 90 times out of 100, 9 times out of 10, you can make a substitution for b. Can you see a possibility for a substitution for b? If I know what h is, can I figure out what b is? B is equal to h times what? 3? 6? What is it? 6? H times 6?
Yeah. If it's 2 meters, it's 12.
Uh-huh.
If it's 1 meter, it's 6.
Yeah. And that'll work for 1 meter, half a meter, 1.5, 1.75, anything up to 2. So that's true. So we could replace b with 6h. So b is equal to 18h squared. Now that right there, all the non-calculus stuff is the hardest part of related rates. Let's talk about it. Did all that make sense?
For the most part.
We'll go back to, like, this is where it all starts. Once we get there, it's all pretty smooth sailing. The hard part about that is even knowing that you're supposed to write that equation. You know you're supposed to write it because they tell you something about dv dt. Okay? That has to do with the problem there. They tell you something about dv dt, so if I had an equation with dv dt in it, I would know something about that equation. If I write an equation that does not involve volume, and I can take the derivative of it, unless them telling me how fast volume is changing winds up being not important, so then I'm just gonna have a difficult time solving that equation. Yeah.
So are there related rates problems where they give you, I can't remember the example, but like they give you 2 different density values, so you have to add like it was height and volume in this, and could you write 2 different equations?
And could you go about it 2 different ways?
Yeah.
So possibly. For the most part, the most straightforward way is one way. I mean, yeah. If there's some other way to go about it, it's going to be some really roundabout, difficult thing. The most straightforward thing you're going to do is say, I know how fast volume is changing. All right, so can I take volume and relate it to, well, they want to know how fast this thing is changing. Can I relate volume to this other thing? So that I can take the derivative so that the rates of change were related to each other. The reason we call it related rates is because rates are in an equation together. They're related to each other by some equation. So all we did was say, well, they tell me about the volume. They tell me something about the volume, how it's changing. They asked me something about the water level, the height of the water. So if they tell me something about the volume and they ask me something about the height, then I must need to relate them in some way. You gotta find a relationship between the two, otherwise, I mean, how do we do any math? We don't find some kind of relationship between these two quantities. So we write this first one, we say the volume of the water part, which is given to be only in the triangular part of the pool. The volume of the water part is equal to, well, it's a prism, so the area times the width. So 1/2 base, we'll write that right here, this is what we're calling the base, times the height, so that's the surface area, times 6 because 6 is the width of the pool. For any base and height, that's gonna give me the volume of the water. But then we said, and we cleaned it up, and then we said, well, it's kind of silly to have to ask what the base and the height are. 'Cause if you know one, you can figure out the other one. The base is always 6 times whatever the height is. You can see that here. It's 1 here and 6. It's 2 and it's 12. Clearly, the height times 6 gives you the base. So you just plug that in for B, 6H, and we get this guy here. Now if we take the derivative, hopefully we'll get something pretty useful. What's the derivative of the left side with respect to time? dv/dt. 36h to the first h dt. Alright, so dv/dt is 1/4 cubic meter per minute. We know that. We know dv/dt is 1/4. Alright, 36 times, do you know the height? It's 1, right? We're talking about this guy right here. There is 1 meter of water. So times 1 times dh/dt, the thing we don't know, the thing we're trying to solve for. How do we solve for dh/dt? Divide by 36. So 1 over 36 times 4? 144 equals dh/dt at that very instant. 1 over 144 what? Meters per minute. Meters per minute.
That's cubic meters, right?
No, that's meters.
That's regular.
That's a height.
Oh, okay.
So it's changing in a matter of meters.
Right.
Alright, 26. Another water tank thing. There we go. Do the work in the black ink. Okay.
Alright.
Think about that for a second. Think about the thing that they tell you about, its rate of change. The thing that they ask you about, probably volume and something else. Think about an equation that relates to that. So the trough is blah, 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 just the dimensions of the trough that are given in the diagram. Ends are isosceles triangles with altitudes of 3 feet. Altitudes are from here to there, it shows you right there, 3 feet. Okay. So just laying out all of the stuff that's given here. So the water is being pumped into a trough at 2 cubic feet per minute. What is 2 cubic feet per minute?
dV/dt.
Oh.
dV/dt, the rate at which the volume is changing with respect to time. dV/dt. So write that down. I may not have any idea why I need to know this yet, but at least I know dV/dt is 2. What is it? 1 cubic. 2 cubic over per minute. Alright, so I know that. If I had an equation that had dV/dt in there, it would just be some variable that I could replace with 2. How fast is the water level rising when h is 1 foot? H is 1, but I only want to, like h is changing, it's actually changing. dV/dt is not changing. The rate at which the height is changing is changing. Height is changing, so I don't want to plug in the height until I take the derivative. Because the height itself is changing. I want to pay attention to this. It's almost step 1 and 2. Write an equation and take the derivative of it. When I write that equation and take the derivative, I want it to include the rate of change that I know, or the rates of change that I know, and the rate of change they ask me about. It needs to involve both those things. If I'm going to have a function, taking the derivative of some function. And it involves the rates of change of, say, volume and of height. And the function I took the derivative of must involve volume and height. Can I write an equation that involves the volume of the water, right? That's what I care about. I don't really care about the whole tank, just the water itself. The volume of the water and the height of the water, do you think they're related? Is there an equation that relates them? I certainly hope so. This seems so what is it? Volume is equal to
1/2 base height width.
1/2 base. Okay, I don't know what that is. Height. These things are changing, right? Okay, but then the width is 12. Always 12. That never changes, so I can just plug that in. Even though when they say when it's 1 foot deep, well, it's 1 foot deep, but it's changing. Right? That's a value that's changing. It's not always 1. It's 1 at an instant. So I don't want to plug that in until I take the derivative. Okay. So they're asking me about how fast is the water level rising. Okay. In terms of like these variables that have been labeled in this diagram, what is the change of the water level? What is that called in terms of DHDT? DHDT is I want to know. Okay. Since I know I want to know DHDT, I know I don't care about B or DDT. So is there another? Like, is there a way to replace B with some expression involving H? B is the same as H? Everybody agree that B is the same as H? It's an isosceles triangle. This guy here is given to be 3, and this is given to be 3. And any triangle that's made by the front side of the water is also going to be a triangle that has, it's going to be a cylinder triangle, similar to the 3 base of 3 and the height of 3. So B is always equal to H, so we can replace B. In H, we get B equals 6. 12 times 1/2, 6H squared. B and H are the same. H times H is H squared. Take the derivative, dV/dt equals 12H times dH/dt. dV/dt, is it known or is it?
It's kind of 2.
It's known. What is it?
2.
It's 2.
Feet per second. Feet squared through.
That's terrible. Hold on, let me write this really big. 2. And do we know what H is? It's 1. That's 12 times 1 times dH/dt. Then I want to know. 1, 6. Yeah, we got 12 here, 12 times dH/dt, 2 over here, 2 divided by 12 on both sides, and 1/6. 1/6 is dH/dt. Is dH/dt 1/6 all the time, always?
That's
At when the depth is 1. When the depth is 1.
Units on
It's gonna take forever to fill us up.
Yeah, what are the units of dH/dt? Feet per minute. Feet, I'm gonna put an arrow at it. Feet per minute. Let's do part B. All that stuff is still back here. Alright. So let's continue on. Yeah.
So, if that's an isosceles triangle,
Yeah.
that means all sides are 3, right?
No.
It doesn't mean that?
That's an equilateral triangle. Isosceles means that has 2 sides that are the same. The 2 sides that are the same are that side and that side. Okay? Da-da-da-da, part B. Part B. So 3/8 inch per minute. What is 3/8 inch per minute? dH/dt. Is 3/8 inches per minute.
When the height is 2.
When the height is 2. 2 what? Okay, so there's some kind of a, we got 3/8 inches and we're talking about 2 feet, right? So we gotta make some kind of a exchange. Times, this times 12?
Maybe. Probably.
3/8 of an inch isn't inches, and I would turn it into feet. What do I do with it? What's, how many, 12 inches, how many feet is that? According to you, it'd say 12 times 12, and it's 144 feet.
Don't do that.
Okay, so what should I do?
Divide.
Divide by 12 inches divided by 12 is feet. So we want to divide this by 12. So we get 1 over 32. 1 over 32 feet per minute. Check my math on that. Don't let me get away with just telling you what's in here. Just don't move it. All right, so DHDT is 1 over 32 feet per minute. That's something we want to know. When H is 2, oh, I can't even see. So H is 2. Determine the rate at which water is being pumped into the trough. I mean, think about that. Your rate at which the height is changing, it's staying constant. It's staying nice and steady. Right? If I want that to stay steady, I have to pump more and more and more water per minute to keep up with it, to keep up with the spreading out of the water as I get closer and closer to this wide opening. So we want to know what is. dV dt is I don't know. All right. They tell us about height. They tell us about dH dt, which is also height. They're asking us about dV dt, which has to do with volume. Right? Remember, our calculus skills come in by writing an equation, taking the derivative of that equation. That's where we get dV dt, dH dt, all that stuff. Well, didn't we already figure out that V equals? We wrote this whole equation, replaced B with H, and it was 6H squared. And, I mean, we took the derivative. dV dt equals 6H dH dt. 12, sorry, 12. 12H dH dt. We know H, we know dH dt. I mean, this isn't even solving, really. It's just computing. Just plug it in, and that tells you what it is. dV dt equals 12 times H, which is 2, times dH dt, which is 1 over 32. This has got to be in the same dimensions, feet instead of inches.
0.75.
Was that? 0.75? 3/4 feet cubed per minute. Its volume is changing, so it's got to be a volume unit. You can plug the units in there. It's all going to work out. Well, let's plug it in. What's 12? 12 what? It's feet. Is that where it came from? Came from 6. Was 6 feet? Yes, you're right. 12 feet. And 2 what? Feet. And 1 over 32 what? Feet. Per minute. There's our per minute, right? Feet times 2 times feet is cubic feet per minute. Eureka. Okay? So, what we're doing now, the next half hour approximately, is just having more time with the same problems, the ones that you had trouble with. Go back, think about, I mean, you got the answers, you know which ones you did wrong, I can put those back up there. Go back and say, all right, I'm going to break down this problem. I know that they're telling me about how fast this is changing. They want to know how fast this is changing. We need to relate them together pre-derivative, right, before the derivative, and then take the derivative. With the added maybe trick of, hey, maybe one of these units, like in both of the cases we just did, maybe B needs to be replaced with H because H is the only thing that I really care about. And the same thing here, it was the same issue. Maybe B needs to be replaced with something in terms of H because I don't really care about it. Take some time with that. I have a couple more problems to get to you. So what we're going to do is just extend this homework assignment. It'll be due next time. And I just have 2 more AP questions on another packet. If you're hanging on to these packets because we will revisit them as we learn more.
Yep.
All right, so
Wait, you know I can't hear. Where's the name here?
this guy. What?
There's a part B. Even though
Here,
I
can
just tell you that it's.
Okay, hold on. Let me do part A first. Okay, so find dy dt when x is 3, given that dx dt is 2. Like we're using these things together. It's not 2 different things. Alright, so dy dt.
Product rule.
Well, we just have a constant multiple, so we can just say 2 times the derivative of whatever that is. What's the derivative of x squared minus 3x?
2x minus 3.
2x dx dt minus 3 dx dt. Right?
Yep, got it.
So x is 3. X is 3. dy dt is 2. Or sorry, dx dt is 2. So 2 times 2 times 3 times 2 minus 3 times 2 equals 2 times 12 minus 6, so 12. So the part B?
Yeah. But there was like, on the answers, it had 2 different answers for part A and 2 different answers for part B.
Did it?
I don't know.
I don't think it did. I think they're crazy.
Number 2.
No, it's just saying like when.
dx dt equals such and
okay,
such.
gotcha.
dy dt equals 12.
Okay, so part,
I'm sorry.
Part B is
Yeah.
x is something else.
yeah, dx dt comes first and it's x equals 1, and then dy dt is second. That
We have to go
equals
to
1,
Thomas class again.
and then dy dt equals 5.
What, we're supposed to find x?
Oh, no, you can't. You can't do that.
No,
It's the same formula.
X equal to 1, not you find dx dt, no.
X is equal to 1?
Yes.
X is equal to 1. And dy dt is 5, so we're finding dx dt.
Oh,
So how come we can't
so do
distribute
you
that?
factor all that out?
So dy dt is 5.
Okay, what up?
2 times 2 times 1 times dx dt minus 3 dx dt.
Probably.
Yeah, just like it, I'll distribute 2, 5 equals 4 dx dt minus 6 dx dt. And factor out dx dt. Dx dt times, well, I really combine like terms, right? So you get a negative 2 dx dt equals 5. So dx dt equals negative 5x. Right? Yeah. Plug in, solve for dx dt.